Wang from the Department of Economics and the Center for Global Business at the Monash University. So this is the seminar series on digital economy, jointly held by Hong Kong Baptist University, Renmin University of China, National Taiwan University, and the Monash University. So before we start the seminar, let me first acknowledge the traditional owners of land. We acknowledge and pay respect to the elders and traditional owners of the land on which our 4 Australian campuses stand. Okay, so we are very happy to have Andrew Rhodes from Toulouse School of Economics as the speaker, and Ta Hao Te from the National University of Singapore as the discussant. Before we have the presentation, let me just recap the rule of the seminar. Andrew will speak for an hour, Ta Hao for around 10 minutes. That will leave up around 15 minutes at the end for Q&A. If you do have any questions, please type them in the chat during the talk. I also stopped Andrew a few times during the talk to take clarification questions. I'll leave broad questions and comments to the Q&A session in the end. So that is everything. Again, we are very happy to have Andrew, who is going to present platform design when sellers use pricing algorithms, with Justin Johnson and Matthias Wildenbeest. Please also notice that it is 6 a.m. in Toulouse, so we are very grateful that Andrew agrees to present his work on this early morning. So, okay, Andrew, the floor is yours.
Okay, let me share the slides. Can you see that?
Yep.
Okay, so thanks very much for the invitation. As Changzi said, this is joint with Justin Johnson from Cornell and Matthias Wildenbeest from Indiana. So I'm going to be relatively brief with the introduction, and I guess I don't need to convince anyone in this audience that many goods and services are nowadays sold through online marketplaces. But moreover, sellers on these marketplaces are increasingly delegating their pricing decisions to algorithms. As one example, even as early as 2015, it was estimated that around 30% of the best-selling products on the Amazon marketplace were priced by algorithms. And that number has probably increased significantly in the last few years with the emergence of a whole industry dedicated to repricing software. Now, this shift towards algorithmic pricing has sparked a debate. On the one hand, there are some who argue that this may lead to fiercer competition because, for example, algorithms make it cheaper and easier for sellers to set prices and then change them in response to changes in cost or demand conditions. On the other hand, other people have raised the concern that actually algorithms may lead to less competition. This is reflected by several recent policy reports, also some cases both in Europe and the US where algorithms were used to implement human-designed collusive schemes. But I think probably more interesting and perhaps more relevant going forwards is some recent experimental evidence by economists that I'm going to come back to a little bit later on, showing that algorithms may learn may learn reward and punishment strategies and therefore sustain high prices even when they were not explicitly designed to do that. Finally, although we're not aware of any direct empirical evidence that adoption of algorithms leads to higher prices, there is some suggestive evidence from a nice recent paper by Assad and co-authors. At the same time, and currently quite separate, there is another debate about platform design, by which we mean the rules of the game implemented by platforms and which affect interactions between users on the platform. There's a lot of interest amongst policymakers on this issue of platform design because these design rules can have an important impact on competition on the platform. Okay, so to take one concrete example, notice that platforms have a lot of leeway in terms of how they rank and ultimately display sellers to consumers. Right? And notice also that because consumers have search costs and there may be other behavioral biases and also just that they're very time constrained, consumers are likely to follow the order that is presented to them by the platform. And this therefore makes it easy for a platform to nudge consumers and ultimately steer demand away from some sellers and towards other sellers. Okay, and this recognition has sparked a debate, especially in Europe, but also elsewhere, about whether large dominant platforms should even have a responsibility to design rules on their marketplace that are pro-competitive. Okay, so in a nutshell, what our paper tries to do is contribute to both of these two debates. In particular, we're going to investigate whether and how a platform might be able to design rules that increase competition on its marketplace. In particular, as you'll see in a few slides' time, we're going to consider simple design policies that, just as I just mentioned, steer demand to a subset of the sellers. Then we're going to do two things. We're going to look, first of all, at the effect of those design policies in theory. And coming back to the first slide, we're going to show that it is indeed important to take into account whether sellers and their algorithms behave in a competitive or a collusive manner. Amongst other results, we're going to show that through appropriately designed steering policies, a platform could completely destabilize collusion, even as sellers or their algorithms become arbitrarily patient. So that's the first thing we're going to do. Then secondly, we're also going to look at the impact of these design policies when prices are set not according to game theory, but set by simple artificial intelligence algorithms. We're going to highlight some similarities, but also we think some interesting and important differences between what theory predicts and what happens when the algorithms actually set prices. Okay, and the bottom line of this research is that I'm going to try and convince you that design policies can indeed be used both to benefit consumers and in certain circumstances, the platform itself. Okay, so I don't want to spend too much time on the literature, but let me just say that this paper contributes to several strands of literature. It contributes in some way to recent papers looking at legal aspects of algorithmic collusion and how we should think about collusion when prices are set by algorithms. There are some recent papers in economics that use theory to look at the impact of algorithms, in particular changes in information. We're going to be most closely related to recent papers, which I'm going to come back to and discuss a bit later on, about experiments with algorithms. So we're going to take a similar setup to some of these papers, but we're then going to add platform design on top. Okay, and I should also say that the theory part of this talk is going to be related to some recent papers on steering and other design issues. One important difference between what these papers are doing and what we're doing is that we're also looking at the case where there may be collusion between sellers. Okay, so with that brief introduction, unless there are any questions, I propose that I go straight into the theory. Okay, so the theory part of this talk is very simple, very light. So this is going to be a game between some firms, consumers, and a platform. So in particular, there's going to be n greater than or equal to 2 firms with differentiated products selling at a constant marginal cost C. These firms have a common discount delta. They interact repeatedly over an infinite horizon, and they do this on a monopoly retail platform. We're assuming that in each stage of this game, sellers set a price. Okay, so in particular, at the beginning of each period, they observe all past prices, and here I say other outcomes. This will become clearer in the next couple of slides, but essentially this means that at the beginning of each period, we observe all past prices and the effect of any platform intervention. Observing all of that information at the beginning of each period, each seller simultaneously sets a price, where seller I would set a price PIT in period T. So that's the firm side. On the other side of the market, in each period, we have a unit mass of consumers, each of whom is interested in buying one product. To make this very easy, we're going to assume that consumers stay in the market for one period, then they exit and are replaced by a new mass of consumers. So consumers get one chance to buy. And otherwise, this is going to be very standard. It's going to be a simple logit model. So in particular, if I as a consumer buy product I in period T, I'm going to generate a utility UIT, which is just equal to a constant A reflecting product quality. I'm going to pay the price, and I'm going to get an individual specific shock, zeta I, for product I. If instead that same consumer takes the outside option in period T, she's going to get a utility U0T equal to another constant A0 plus an individual specific shock, zeta 0. And as I said, we're going to assume that zeta 0 and each of these zeta I are IID draws from a type 1 extreme value distribution with parameter mu. So we're going to end up with logit demand with parameter mu, where a higher mu is going to mean that there's more differentiation between these sellers. Okay, and as I said, the final ingredient is that these products are listed on a platform. So to do this in a simple and tractable way, we're going to assume that in each period, the platform chooses a subset of these sellers, displays them to consumers, and consumers can only buy from that subset of sellers. So this is trying to get at a simple way in this idea that the platform can nudge consumers and therefore steer demand away from some sellers towards others. Okay, and during this talk, I'm going to look at two different ways in which this subset of displayed products could be generated. I'm going to have a very simple rule that I'm going to tell you on the next slide. Then I'm going to have a slightly more subtle rule that I will discuss in a few minutes' time. Okay, so the first design rule that we're going to look at is very, very simple. This is called price-directed prominence, or PDP. And all this says is that in any period of the game, the platform is going to look at all of the prices being set by the sellers, and it's going to choose some number K that it chooses and commits to that up front, and it's going to display K of the firms with the lowest prices. Okay, and if ever there is a tie for the Kth lowest price, then the platform is going to break those ties randomly so that exactly K sellers are shown. Okay, so we're going to first of all look at the effect of this very simple design policy. And again, coming back to the first slide, it's going to be important to distinguish between whether sellers in this marketplace behave competitively or cooperatively. Okay, so let's first of all look at the case where sellers behave competitively, by which we mean that in each period, sellers behave as if this was the only period that they're actually in the market. Now we know that without PDP, so without any intervention, all N firms will be displayed. And we know that there's a unique Bertrand-Nash equilibrium price, PBN star, which strictly exceeds marginal cost because of product differentiation. Now with price-directed prominence, only K firms are going to be shown, and it's easy to argue that these firms are going to Bertrand compete for the right to be amongst those K firms that are displayed to consumers. Okay, so in other words, when we introduce PDP, firms compete down to marginal cost. Okay, and therefore, very simply, PDP represents a trade-off for consumers. They pay a lower price, they pay marginal cost instead of PBN star, but they're exposed to less variety. They can only buy K variety, they can only choose from K varieties instead of N varieties. Okay, and therefore, it's not surprising that we can generate this simple cutoff result, which says that compared to the case where there is no intervention, so all N firms are displayed, PDP is going to raise consumer surplus if and only if the fraction of firms that is displayed, K over N, exceeds a threshold. Now we have more detail in the paper, but one can show, for example, that this price effect is so strong that this simple intervention will benefit consumers even if almost 2/3 of the firms are being obscured or hidden from consumers. And so, for example, if K is equal to N-1, so only one firm is hidden, then one can show that consumers always gain. Okay, so in a competitive market, if it's used appropriately, this intervention can perform very well for consumers. It turns out that's not necessarily the case when the market is cartelized. So to illustrate that as simply as possible, we focus on what we call a full collusion benchmark, meaning that when sellers are colluding in this marketplace, in each period they set prices in such a way as to maximize total industry profit. Now, as is standard in this kind of game, collusion is going to be easier to sustain when sellers are more patient, so when delta is higher. Now, it's straightforward to show that full collusion is easiest to sustain, so it can be sustained for the widest range of delta when two things are true. Firstly, in each period of this game, all of the firms charge the same price, which is going to be the same price as a K product monopolist would choose. They do that until there is a deviation. And then after a deviation, the firms play the one-shot Nash equilibrium that I had on the previous page and therefore just charge marginal cost. Okay, so intuitively, why is this? Well, this first bullet point ensures that because all of the firms are charging the same price in each period, it's the platform who randomly decides which sellers should be displayed. And so this means from an ex-ante perspective, firms share the demand equally in each period. So this intuitively, this maximizes their benefits from participating in the cartel. And secondly, because after a deviation, they play the one-shot Nash equilibrium forevermore, that means that they get zero profits after any deviation. And so this minimizes their incentives to deviate. Okay, so this is what happens under full collusion. Okay, and therefore, assuming that we play this kind of equilibrium, let delta k hat be the critical discount factor, such that full collusion is sustainable if and only if delta exceeds that level. Okay, and then we can again show a very simple result, which says that condition on using some PDP, so condition on having this intervention, full collusion is harder to sustain when you show fewer products, in the sense that as you show fewer products, this critical discount factor, delta k hat, increases. And again, the intuition for this result is very simple. Think about a case where I reduce the number of firms that I show. Well, firstly, because fewer firms are being shown, the monopoly profit, and therefore the joint collusive profits, are lower. Okay, so the incentive to participate in the cartel is lower. At the same time, one can also show, this requires a little bit more work, one can show that the best one-shot deviation from collusion is higher when K is lower, so when fewer firms are being shown. So the intuition is that if I as a firm undercut the cartel, and I still demand, well, if K is lower, I'm being displayed alongside fewer other firms, and therefore my demand and so my profit is going to be higher. So because of these two channels, we can indeed show that a more aggressive implementation of PDP, meaning that K is lower, does indeed mean that collusion is going to be harder to sustain. However, at the same time, we think it's also interesting to think about the case where delta is perhaps very high. Why? Well, one thing that we might think algorithms will be very good at is responding quickly to changes in prices by other firms. And in the model that we have here, that's kind of equivalent to delta being very high. Okay, so let's assume that the discount factor delta is sufficiently high so that full collusion can be sustained with or without this platform intervention. Then we get another simple result, which says that when we implement PDP more aggressively, so when we show fewer firms, well, prices go down, but now, in contrast to what we said for the competitive market, consumer surplus also goes down. So the intuition for why prices go down is again very simple. Remember here, prices are the same as what a multi-product monopolist would charge. And if a monopolist has fewer products, it's less worried about cannibalization, so it charges lower prices. But it turns out here that those lower prices are not enough to outweigh the loss in variety suffered by consumers. Okay, and so I will pause for questions in a minute, but let me just wrap up this part of the talk. So we've looked at this very simple intervention where I just show the K products with the lowest prices. We've shown that such an intervention could work well in a competitive market, but could potentially go badly for consumers in a cartelized market. Okay, now what I want to talk about is the more subtle platform intervention. But before I do that, maybe let me pause and see if there are any quick questions.
So Andrew, I do have one quick one, if I may. So this is a very benevolent platform you just described here. Mm-hmm. Think of a platform that seeks to extract surplus from sellers, right?
Exactly. So that's what I'm going to come to towards the end of the talk. Yeah.
Okay, no worries.
So there's a question in the chat.
Mm-hmm.
Does this mean consumers are invariably taken for a ride?
In what sense? So it's true that the platform. So in this very simple intervention, it's true that the platform is limiting choice. So this would mean that ex post a consumer might complain that they didn't have access to all of the varieties, or it was hard to find all of the varieties. But as we can see in the competitive case, it doesn't necessarily mean that consumers are being harmed. They might actually benefit from having their choice limited. I guess that's the main takeaway from this particular intervention. I'm not sure does that answer the question?
Yes, what I meant was that, we always have this suspicion that all these big companies would use algorithms to kind of set prices, because they are such in a monopolistic or monopoly kind of position, and consumers are increasingly unable to live without them in a way, right? So, on a long-term basis, if they are not being controlled, consumers will invariably get a raw deal in most cases. That's where I'm coming from. Yeah, Professor Andrew.
I see. So I guess here, so I'm going to come to what happens in the experiments when we actually use algorithms later on. But I guess here you should think of it as the sellers maybe using algorithms to price, and that may be leading to collusive outcomes. But we can also think that the platform also has an algorithm. And we're looking at how we can design the platform's algorithm to potentially benefit consumers and overcome any harm that is caused by the sellers using algorithms. I think that's maybe the best way to think about these results.
Okay, thank you.
So I think that also the story also heavily depend on the assumption of product differentiation, right? So have you thought of like the homogeneous product with like a Kuno competition, things like that?
So homogeneous goods, but with Kuno.
Yeah. You wouldn't have those like when you have a more one thing is that the variety, the number of varieties no longer matters, and then also the there's cannibalization, the price increase with more varieties also won't be there.
So I guess in a platform context, I would maybe be a little bit worried about using Kuno. I didn't say anything about this mu. So this mu could be very small. So it could be the case that products are very close to being homogeneous, and there's just a very tiny amount of differentiation. All the results that I'm showing you will still go through.
Yeah. Okay. I think you can move on.
Andrew,
okay.
I have a question. So you have a result about the price when there are fewer products being shown, the price will be lower. And you restrict that particular result to the case when the platform is very patient, or the sellers are very patient. Intuitively, why wouldn't or would the result extend to more generally, just because of your intuition that when there are fewer products being shown, it is more difficult to sustain collusion, and hence the price being sustained in a collusive equilibrium would be lower. Would that particular pattern hold in generally for any level of patience?
Yeah, so it's true that here I'm showing you results just for, you could think of these as very impatient firms, so who are behaving competitively, and there we see that prices come down. And I also showed it to you for the case where sellers are very patient. Of course, in general, we know that there are going to be a lot of potential equilibria here. So that's why I'm just focusing on these two extremes. I think probably more interesting will be when I get to the experimental results. So when we actually have these algorithms setting prices, we'll see something very close to what you just mentioned happening.
So instead of just talking about the two extreme case, for general, I know that you think that patience is actually the relevant case in practice, but theoretically for general level of patience, what do we note about welfare? So in the very patient's case, you said that limiting the number of products is almost like a multi-product firm not being able to show more product, and hence welfare is going to decrease, or consumer surplus is going to decrease. But more generally, how does the limitation on collusive power and the loss of variety, how do they trade off?
Yeah, so I think the problem with doing it in general away from those two extremes is that we know that there could be many equilibria in this collusive super game. And so it could be that with one set, suppose I show all of the sellers, they play one equilibrium. Now suppose I show fewer sellers, then maybe we're going to jump to another equilibrium. So it's hard for me to really think about how that equilibrium is changing, given that we have to do selection. So that's why I was sort of focusing on this case where delta is very high. So I think it's reasonable as a benchmark case to select this fully collusive outcome where they set monopoly prices in each period. But of course, there are also other equilibria, right? We could alternate between a high price and some other price. We could play very complicated collusive schemes. So that's why I deliberately tried to avoid getting into that issue.
Yeah, right. Okay, thanks.
So should I go on?
Yes.
Okay, so that was a very simple intervention. So just to recap, we saw that intervention could work well in a competitive market, may work less well in a collusive market, again, coming back to the question, depending upon how we do equilibrium selection. So for that reason, we then look at another intervention, which we call dynamic price-directed prominence, or dynamic PDP. So I'm going to give you the formal definition on this slide. But before I do that, let me just say intuitively what we're trying to do here. So we're trying to come up with a simple platform rule here that rewards sellers who set low prices, not just with higher demand today, but also with higher demand in future periods as well. So if a seller sets a low price today, they get rewarded today, but also in the future. And so you can sort of intuitively see that that's going to make it more attractive for firms to deviate from a cartel. And so, as I will show you on the next slide, this intervention can potentially completely destabilize collusion. Okay, before I get there, let me go through the formal definition of this rule. So this rule is more subtle than the one that I just looked at. So dynamic price-directed prominence works in the following way. In the initial period, t equals 0, the platform looks at the prices being set by all of these sellers, and it picks out one of those firms that has the lowest price. Okay, having identified that firm, or one of those firms with the lowest price, the platform then does two things. Firstly, it's going to display that firm to consumers in this period. And secondly, it's going to confer upon that firm an advantage going into the next period. Okay, then in period 1, and indeed in all future periods, going into that period, there is going to be some firm, let's call it firm I, who is holding this advantage. Okay, then what the platform is going to do is it's going to check two things. I'm going to look at this firm with the advantage, and I'm going to check, number one, has that firm raised its price compared with the previous period? Secondly, I'm going to check, is firm I being undercut by some other firm by more than a fixed advantage ADV, where ADV is just some number that the platform the platform is going to check this for this advantage firm, firm I. Okay, so imagine that firm I in some period T, firm I has the advantage going into that period. If number one, firm I has not raised its price compared with the previous period, and secondly, if firm I is not being undercut by any other firm by more than this advantage ADV, then the platform does two things. Firstly, it continues to display only firm I to consumers, and secondly, it also gives firm I an advantage going into the next period. Now, if on the other hand, in period T, the firm holding the advantage, firm I, does not satisfy these two conditions, so either the firm has raised its price compared to the previous period, or it's being undercut by another firm by more than this advantage ADV, then it's as if we're in the initial period. So the platform, again, puts all of these firms on an equal footing. It looks at all of the sellers' prices. It picks one firm with the lowest price, displays that firm, and gives it the advantage going into the next period. Okay, so I hope this is clear, but in case not, let me just quickly recap. So the idea is that in the initial period, we look at all of the prices, we find one firm with the lowest price, we display that firm, and we give that firm an advantage. Then in all future periods, going into such a period, I'm going to have a firm that's holding this advantage. That firm is going to continue to be displayed and also keep the advantage, provided one, that firm hasn't raised its price compared to the previous period, and two, if that firm isn't being undercut by too much. There's some leeway. So even if this firm is undercut a little bit by another firm, it still keeps the advantage. But if it's undercut by enough, where that enough is this ADV, which is set by the platform, then the advantage is taken away. Okay, so if the advantage firm has raised its price or it's being undercut by a lot, then it loses that advantage, and that advantage is potentially given to someone else. Okay, so note that the idea here is that in the initial period, all of these firms are treated equally, symmetrically. They all have an equal chance to be the firm that is displayed prominently to consumers. But after the initial period, a firm that set low prices at the beginning So did you mute me, Shengxi? Okay, so can you still hear me?
We can hear you.
Okay, I think it muted me for some reason. But okay, so is everyone clear on this, on intuitively what this rule is trying to do? It's trying to reward firms we set low prices, not just with higher demand at the beginning, but also in future periods as well. It makes it easier for a firm that sets a low price at the beginning to also get demand in the future. Okay, now because of this, one can prove the following result. So first of all, one can show that collusion is harder to sustain in the sense that it's sustainable for a lower range of discount factors compared to when we had just regular PDP, the intervention that I showed you earlier. One can also show that when this ADV, this advantage set by the platform, is sufficiently large, then actually collusion is impossible, by which we mean that for any discount factor strictly less than 1, in any pure strategy subgame perfect Nash equilibrium, the transaction price is going to be marginal cost in all periods. So for a sufficiently high ADV, sellers can't collude at any price that exceeds marginal cost. Okay, so the intuition comes back to this idea that dynamic PDP seeks to reward firms with low prices, with higher demand, not just today, but also in the future. So intuitively, this means that firms have more of an incentive to undercut a cartel, because if we're trying to, suppose we're trying to sustain this very high monopoly price, if I as a firm cheat on that by undercutting, then I get more demand today. But because of this ADV, it's harder for firms to punish me in the future. So I'm guaranteed some demand at a price above marginal cost, even in future periods. I haven't put it on the slides, but we can also show, therefore, that because dynamic PDP potentially reduces prices from this very high monopoly level down here to marginal cost when ADV is sufficiently high, it's easy to show that this intervention can work very well for consumers. Okay, so again, just to sum up, we've looked at these two simple design rules. The first one, PDP, can work well in competitive markets, less well in collusive markets. Then we have this other intervention, dynamic price-directed prominence, which can perform very well even in cartelized markets. Okay, so that's all I want to say for the theory. What I want to do now is discuss a little bit about what happens when prices are set by algorithms rather than in theory. Okay, before I do that, again, let me just pause and see if there are any questions.
Andrew, intuitively, if I'm just too slow to think through, intuitively, if you you have an algorithm that is the n-1 firms in that is being in advantage instead of one firm, what would happen?
So in this case with dynamic price-directed prominence or in general?
Just the dynamic PDP. So instead of just having one single firm having advantage, you just exclude one firm and let n-1 firms coming in and continue to be shown and continue to be having an advantage until they are raising prices or being undercut by the remaining firm.
So we never actually looked at that formally, but we sort of have the intuition that we're going to get the same result here, at least when this advantage is sufficiently large. So we think we could probably prove that we're going to get the same result. And obviously, this conclusion here that consumers benefit would only be strengthened, because then you would get the benefit of this very fierce competition, but you would be exposed to more variety. So although we don't have a formal result in the paper, we're pretty confident that we're going to get the same result here.
So
and therefore this result will be strengthened.
Wouldn't the n-1 specification be the natural starting point, given that it is not sacrificing too much variety? I'm just wondering, I was under the impression that you started with this extreme form, which has a severe loss of variety, is because the collusion advantage is coming from this particular extreme form.
So I agree, it might be natural. On the other hand, what you can, so we have a more formal result in the paper, which I didn't put in here, but one can show that even when n is very large, consumers benefit under mild conditions. So in a sense, I think this result is more striking. I only show one firm, but when I have this particular platform design rule, consumers benefit under mild conditions. So even when the loss of variety seems to be quite large.
I see. Yeah, thank you.
Okay, shall I go on? So I think I only have about 25 minutes, is that correct?
Yeah, you have 20, yeah, about 25 minutes.
Okay, so maybe I'm going to skip some material. So what I wanted to do in the rest of the talk was now turn to the experimental part. So I probably won't go through all of the details here, but I just want to give you a flavor of the algorithms that we actually use when we run our experiments. So in our experiments, we're going to use simple artificial intelligence algorithms called Q-learning algorithms, which learn how to price based on their past experience in the marketplace. Okay, so before I go into some of the details, why might we use such algorithms? Well, if you look on Google, it's very easy to find examples of repricing software companies who at least claim that they use artificial intelligence in their software. So here is a company, a screenshot from a website of a company called Aura, who provide repricing software for sellers on Amazon. Okay, and they certainly claim to use AI. If you scroll down their website, there's lots of interesting stuff on there. One thing here is that they make the claim that because they use AI in their pricing software, the more you use that software, the more effective it becomes. So this could just be a marketing ploy, but it is also consistent if they are using AI, in the sense that the algorithm is slowly learning from its experience in the marketplace and is therefore providing a better pricing service for the firm. Now, of course, a lot of these companies like Aura claim that they use artificial intelligence. We as researchers can't check whether that's really the case, or if it is the case, how sophisticated the algorithms are that they're using. On the other hand, we do know that AI is being used in a wide variety of applications, including solving complex problems like, as I've got here, designing a computer program capable of beating multiple world champions at board games such as Go. So the point I'm trying to make here is that AI is being used in a wide variety of applications to solve very complicated problems. And so it doesn't seem crazy to us to imagine that in the near future, many companies like Aura will be using quite sophisticated AI to help sellers with their pricing problems. Now, why do we focus on Q-learning in particular? So I'm going to tell you a bit more about Q-learning in the next few slides. Q-learning is very popular with computer scientists, and it's also been used recently in a couple of economics papers. It's related to reinforcement learning algorithms, which are a building block for things such as the Google DeepMind's AlphaGo program, which beat the world champion here. So I think it's reasonable to focus first of all on AI algorithms, and then we think it's natural to look at Q-learning, given that it's a building block in many real-world applications when AI is used. Okay, now I don't have so much time, so I'm not sure how much I want to spend on this. So here I was going to try and give you an overview of how Q-learning works. So maybe let me just go through this quickly. So to illustrate Q-learning, let's first of all start with an abstract setting where I have one agent with some finite action set script X and some finite state space script S. Okay, and imagine that when this agent is in state S and she plays an action X, she's going to get some payoff pi S of X. Okay, and imagine that the transitions from one state to another could be probabilistic, and they may potentially depend both upon the current action that the agent is playing and of course the state that she's currently in. Okay, imagine that this agent wants to maximize her total discounted payoffs, but initially she's uninformed both about this payoff function here and the transitions between states. So Q-learning is a simple algorithm that's going to help her learn how to maximize these total discounted payoffs. Okay, so in particular, under Q-learning, we're going to iteratively estimate what is known as an action value function, Q star S of X. Okay, so this is going to be a matrix which is going to tell me if I'm in state S and I take action X, what is my discounted value of doing that? Okay, so this is just going to be a matrix, but notice that if we could recover this matrix Q star, then we would know the optimal policy, right? Because for any, suppose I represent states by rows, given that I'm in state S, I just read off that row on this matrix. I can look at my discounted payoff from playing each of these actions, and then I just pick the action which maximizes that payoff. Okay, so the question is, how do I get to this action value function, Q star? Well, the idea in Q-learning is the following. So you would start off with some initial, perhaps arbitrary matrix, Q matrix. And then as I let time run, suppose that in time t, we're currently in state S. So what Q-learning does is it mechanically forces the agent to either experiment or exploit. In particular, with some probability epsilon t, in period t, the agent is going to be forced to experiment. And the simplest way to do that experimentation is to just randomly pick an action from those that are available and see what happens. With complementary probability 1 minus epsilon t, Q-learning forces the agent to exploit, which means that the agent looks at this current Q matrix. Given state S, she reads off that matrix, what is the best action that I should take at the moment, and the agent takes that action. Now, whether the agent experiments or exploits, in state S, after taking some action X, then she's going to realize a payoff, and she's going to transit to another state S prime. Okay, and then the key thing is that now that we've played that action, we've got some more information, right? We've learned a payoff, and we've also learned what state we've transited to. Okay, so the idea is that then I'm going to take the original cell of the Q matrix corresponding to the state S I was in and the action X that I took, and I'm going to take out that value and I'm going to replace it with the information that I just got. In particular, the way we do that is that there is some parameter which the researcher specifies, an alpha, which is how much weight I put on the new information. So in particular, so this notation is just taken from computer science. So this says that I take the value in that cell of the Q matrix that I had before. I put a weight 1 minus alpha on that. And then I put a weight alpha on the information that I just got. And what information did I just get? Well, I got a flow payoff. And then I can look at my original Q matrix and I can work out, given that I've transited to state S prime, what is my value, or what do I think is my value from being in state S prime, given that I'm going to take, assuming that I would then take the greedy action that maximizes my discounted payoff. Okay, then the agent has now transited to state S prime. In the following period, t plus 1, starting from state S prime, she's going to do exactly the same thing. Okay, so I know that this is a little bit quick, but the idea is just that this algorithm is mechanically sometimes exploiting, so doing what we think is the best thing, but sometimes experimenting, trying out new actions and to see what happens. Then there is some updating process, which is governed by a parameter alpha that the researcher specifies. And to cut a long story short, one could show that in simple settings with a single agent, then you'll get convergence to the optimal action under very mild conditions. Even in multi-agent settings like we have, where we have multiple firms, each of whom has an algorithm which is trying to learn an optimal pricing strategy, you typically also get convergence. Okay, so I want to go through this quite quickly because I want to show you some results. But just to say that we're going to take this Q-learning and we're going to put it into this setting with multiple firms and platform design. The basic setup, including the parameterizations, I have more details in the appendix, but the basic setup is going to be very similar to in a recent AER paper by Calvano and co-authors. The main difference is that we're also going to, of course, allow for platform design. So we're going to look at the effect of those design rules that I showed you earlier. One important difference with the theory model that I showed you earlier is that we're going to introduce another parameter, gamma, which is supposed to capture the extent of platform design. So in particular, we have in mind that we're going to split the population into two groups. There's going to be a group, a fraction gamma of consumers on whom PDP or dynamic PDP is implemented. So they see a restricted set of firms. But on the remaining fraction, 1 minus gamma of the population, they just see all of the firms. So they're not exposed to BDP. So clearly, if gamma is equal to 0, this is just a regular case without platform intervention. Gamma equals 1 is just the case that we looked at in the theory model, but we're also allowing for anything in between as well. There are a few other details here which are perhaps not too important, so I won't spend too much time on them, but all this is saying is that we're going to have to discretize the price grid. And if you remember what I said about Q-learning, we have a state space. So in our application, the state space is going to be the prices that were set by firms in the previous period. Okay, but that's probably not too important, so I'm going to skip that. Are there any quick questions before I go to the results? Okay, so if not, let me show you a few basic results using these two interventions. So first of all, as a benchmark, we think it's important to look at the case of what happens if there is no intervention. So in other words, gamma is equal to 0. So I have a few results here. Let me focus perhaps on this top panel. So this is the case where I have two firms initially. Discount factor is 0.95, so relatively high. And let's set the parameter in the logit model equal to 1/4. Now, if we run this, we find that theory would suggest that the Bertrand-Nash price should be around 1.5. Theory would predict that a fully collusive cartel would end up charging a price of around 1.9. And when we actually run these algorithms, they end up settling on a price of around 1.7. So this is very consistent with earlier work that didn't look at platform design. You can see here that the algorithms are ending up charging somewhere roughly halfway between the competitive outcome and the fully collusive outcome. So without any platform design, the algorithms are going to end up charging relatively high prices. Okay, so now the question is, what happens when we introduce those two simple design rules that I showed you earlier? Okay, so let me start with price-directed prominence. So this slide is again looking at the case with two firms, discount factor 0.95, logit parameter 1/4. I'm going to talk about what happens when I change all of these parameters shortly. Okay, but for now, let's just fix this particular constellation. So what these two plots are showing is respectively share-weighted prices being charged by the firms and consumer surplus. And in both cases, on the x-axis, I'm plotting gamma, the fraction of consumers who is only shown one product. Now, in the red curves here are showing what happens to prices and consumer surplus in theory for a fully collusive cartel. That's just as a benchmark for you to compare. And then the blue line here is what the algorithms are actually playing. Okay, so if you look at this plot here, this is saying that if I start at gamma equals 0, so no intervention, and I start increasing gamma, so there's more platform intervention, then initially the algorithms start to increase their price a little bit, but eventually price falls. And comparing no intervention with full intervention, so like in the theory model, prices end up being around 7% lower. At the same time, if I look here, this is what happens to consumer surplus. You can see that consumer surplus is also slightly non-monotone, but the important thing again is that if I start at gamma equals 0, no intervention, and then I go to gamma equals 1 full intervention, consumer surplus ends up lower. Now, recall that in the theory model, we said that for a fully collusive cartel, we would expect PDP to lower prices, but also lower consumer surplus. Now, given that we have a relatively high delta, this seems like it could be a reasonable candidate for a market that would be at risk of collusion. And this slide is very consistent, therefore, with what theory says. PDP reduces prices. We start up here and we come down to here, but it also reduces consumer surplus. Consumer surplus starts here and it finishes here. Now, I don't want to, I mean, in the paper, we have a lot of different experiments for different parameterizations. I can't go through everything. What I want to do with this slide is just to tell you that, make the point that it's not always the case that the algorithms do what theory would expect. Okay, so just to illustrate that in one slide, I've taken exactly the same setting as before, but I've lowered the differentiation parameter. So now products are more homogeneous compared to the previous slide. But again, delta is high, and so we might think that this market is a good candidate for collusion. Now, what happens here, again, if I start off with no intervention, gamma equals 0, and I go up to gamma equals 1, you can see that there's this non-monotonicity, but overall prices end up being lower, as theory would predict. The difference now is that actually, when I go from no intervention here to gamma equals 1 full intervention, consumer surplus actually ends up being higher. Okay, so this is contrary to what theory would predict for a fully collusive cartel. Okay, so again, this is just to make the point that the algorithms don't always do exactly what the theory suggests should happen. I'll give you more examples if I have time in the next few slides. But what I propose to do now is just focus on what I did in that first panel and on that first slide, which is to look at this case with relatively high differentiation. Okay, and what I want to do now is show you what happens when we vary the discount factor. So you remember that in the theory model, we said that the performance of PDP seemed to depend crucially on whether sellers were behaving competitively or collusively. Now, our sort of intuition here is that if the discount factor delta is relatively low, then that might suggest a market where sellers are going to behave relatively competitively. Whereas if delta is relatively high, that may suggest that sellers may behave more collusively. Okay, so that's kind of what we want to get at here. So this first plot here shows gamma, the proportion of consumers shown one product, against the discount factor delta. And here we're just looking at the level of consumer surplus. So if you look at this plot, you'll see that red colors mean that consumer surplus is relatively high, and blue colors mean that consumer surplus is relatively low. So if I pick a particular value of gamma and I move up, then that means that I'm slowly increasing the discount factor delta, and you can see that the level of consumer surplus is monotonically decreasing. Okay, so first of all, this sort of suggests that the algorithms are behaving sensibly. This is saying that when delta is low, then they're behaving quite competitively. Consumer surplus is high. As I increase delta, it seems like they're able to sustain higher prices, and therefore the level of consumer surplus is lower. Okay, so this is sort of like a sanity check that they're doing sensible things. The second plot here then looks at not the level of consumer surplus, but percentage changes in consumer surplus. So if, for example, I take a gamma of 0.7 here, and let me take this point here with delta equals 0.5. So what does this represent? So the number here would be the percentage change in consumer surplus when I go from gamma equals 0 to gamma equals 0.7. And again, red colors mean that consumer surplus has gone up, blue colors mean that consumer surplus has gone down, and green colors mean that it hasn't changed very much. And again, what you see in this plot is that when delta is relatively low, so we think the market is relatively competitive, indeed, PDP is increasing consumer surplus. It's only when we get to very high discount factors up here that we start getting these blue colors, meaning that PDP is lowering consumer surplus. Okay, so what you should take away from this diagram here is that unless delta is very high, and so we think there's a significant risk of collusion, PDP does seem to be improving consumer surplus, okay, which is qualitatively like what the theory model would predict. Okay, so with that in mind, now let me go back to this case of a high delta, okay, where we saw that PDP was not performing very well. And let's look at what happens when we introduce our second intervention, dynamic PDP. So again, I'm plotting share-weighted prices here and consumer surplus here against gamma, the fraction of firms that is shown one product. The blue lines here, these are just copied from a couple of slides earlier. That's just outcomes when the algorithms are pricing an environment with PDP. And the red line is what happens with dynamic PDP. So remember, dynamic PDP is the second more subtle intervention that we looked at. Okay, and what you see from both of these plots is that in general, when we have this second intervention, dynamic PDP, first of all, prices for any given level of gamma, prices tend to be lower. So sellers are competing more fiercely. And therefore, perhaps not too surprisingly, consumer surplus is therefore higher. Moreover, if I start with the case where gamma is equal to 0, so I have no intervention, we can see that this second intervention generally leads to higher consumer surplus. Okay, so that's the first thing. So we've seen that this simple intervention PDP tends to harm consumers when delta is relatively high, but this more subtle second policy can benefit consumers. And I have some statistics here. So if you go from no intervention to gamma 0.99, then consumer surplus can be as much as 23% higher in this particular experiment. Now, what is interesting in these pictures is that you can see that there is a sharp changing behavior by the algorithms around gamma is equal to 1. So in particular, as I increase gamma, prices here are smoothly falling. Okay, there's obviously some noise here, but they're basically falling. And then there's a big jump up at gamma equals 1. So a big jump up in prices, and therefore a big jump down in consumer surplus. Now we attribute this to a learning challenge. Right? And by that I mean the following. So notice that when gamma is equal to 1, that means that all of the consumers are being treated with dynamic PDP. Okay, so this means that if you're the firm who doesn't have the advantage, remember ADV gives a cushion to the advantaged firm. So even if I undercut the advantaged firm by a little bit, if I don't have the advantage, I won't be able to get any demand. Right, that's the whole point. That dynamic PDP gives this cushion to the advantaged firm. So this means that if gamma is equal to 1 and I don't have the advantage, then there's going to be a wide range of prices where I may not be able to get any demand. Okay, and we think that that basically messes up the algorithms, makes it hard for them to learn. It certainly means that they don't have incentives to charge low prices, so it seems that they just revert to charging high prices. To get at that a little bit, I don't have much time to talk about this, but we do something which we think is quite interesting, which is we then augment the state space. Remember, I said very quickly that in our experiments, the state space is just the prices that were charged in the previous period. Now, given that we have this learning challenge, it seems natural to perhaps augment the state space by adding the identity of the firm that actually has the advantage. So that's what we're doing on this slide. So here, the blue line is just regular PDP. The red line is dynamic PDP from the previous slide. And this curve here is what we call a smarter AI, where we augment the state space by including the identity of the firm that has the advantage. Okay, and what you see is that prices tend to be lower, consumer surplus tends to be higher, but more importantly, we don't get this sharp discontinuity around gamma is equal to 1. So that confirms our suspicion that here this discontinuity was being caused by this learning challenge. Okay, so I'm almost out of time, but are there any quick questions before I go to some extensions and I talk about profits? Okay, so if not, I won't go into exactly what we do here, but let me just say that we do a lot of robustness checks in the paper. So you remember when I introduced Q-learning, I said there were these parameters that that determined how much exploitation there would be and how much updating there would be. So in our baseline analysis, we follow that Calvano et al. AER paper, and we pick exactly the same parameters as they do. But we've also checked that when we change these parameters in the algorithm, that we get qualitatively similar results. When I did dynamic PDP here, I was picking a particular value for this cushion, this ADV. So we've done some robustness checks with different values of ADV, and we found some interesting differences with what theory predicts, which maybe I could discuss later after the talk. And we also vary the number of firms. Okay, but I think the last thing that I should talk about quickly is platform profits. So remember I said at the beginning, there's this debate that perhaps large dominant platforms should be compelled to design rules which lead to more competition on their marketplace. So that's what we focused on so far. But of course, it's important to think about what is the effect of these interventions on the platform's profits. Now, clearly, that depends on how the platform actually generates profits, right? Depends on its business model. But we note that in practice, platforms often levy per unit fees, but also revenue sharing fees. And so, for example, if you're a seller on Amazon and you use its fulfillment service, you're going to pay a mix of these two fees. Okay, and so therefore, generalizing a little bit, it seems reasonable to imagine that the platform may benefit from these design rules if they lead to overall an increase in seller revenue or the amount of output, the number of units that is traded on the platform. Now, in turn, revenue and output could go up if per consumer revenue and output go up, but also even if those things go down, note that overall revenue and output could go up if the platform manages to implement rules which increase consumer surplus and therefore draw more consumers to the platform. So either I might benefit on a per consumer basis, or I might be able to attract more people to the platform. Okay, now in the paper we have results about what happens in theory, how those design rules affect both output and revenue. But here I'm just going to focus very quickly on some results from our experiments. Okay, so let's first of all look at per consumer revenue. Now it turns out that although in theory the interventions could increase per consumer revenue, in our experiments for the particular parameters that we choose, revenue always actually decreases on a per consumer basis. Okay, and so this leads us in the paper to look at what we call a critical growth elasticity, which precisely says what is the percentage change in user base from a percentage change in consumer surplus needed for the platform to become whole again. Okay, so again, when we implement our design rules, per consumer revenue falls, but consumer surplus may increase. Okay, and so if consumer surplus increases, we might expect more consumers to join the platform. And so this critical growth elasticity is trying to get at how much extra, how many extra consumers we need for the platform to benefit from this intervention. So here I have the results from a few specifications. So with PDP and dynamic PDP, we have more stuff in the paper, but this is just a few. So we're varying the discount factor, we're varying the number of firms. So here, first of all, we're looking at values of gamma. So remember, gamma is the fraction of consumers who are exposed to these interventions. We're varying gamma between 0 and 0.99. And we're looking at, first of all, the percentage of those values such that consumer surplus goes up. And you can see in some cases that's very high. So consumers tend to benefit from these interventions. Revenue, as I said, never goes up, but we can compute this critical growth elasticity such that the platform overall benefits if it's being remunerated based on revenue. We can then do the same exercise with output, and here we get much more favorable results for the platform. So again, I have those same specifications. Now you can see that for a lot of values of gamma, total output output on a per consumer basis increases. We can again compute this critical growth elasticity. And when I say 0 here, I mean that because a gamma equals 0.7, actually both consumers are benefiting and output per consumer is going up. Okay, and so there the platform is certainly benefiting from this intervention. So I know I went through this very quickly, but the point I want to make here is that we see both in theory and our experiments that consumers can benefit from these interventions. Depending upon the platform's business model, it may also benefit from these interventions, either in some cases because per consumer, for example, per consumer output goes up, but also sometimes, even if that falls, it could be the case that the platform benefits if it can attract a relatively small number of extra consumers to come to it, and that may be possible because there's increasing consumer surplus. Okay, so I think I'm out of time, so let me quickly conclude. So we've looked at simple design rules which steer demand away from certain sellers towards others. We've shown that in competitive markets, even very simple policies may benefit consumers, both in theory and in the experiments. But when there's a risk of cartelization, more subtle policies may be required. Now, of course, we're looking at very simple policies here. This is a very stylized model, but hopefully this gives some food for thought and convinces you that there may be a role for platform design in raising consumer surplus. And hopefully, although I went over it very quickly, I've also managed to convince you that there's not necessarily a trade-off between platform profits and consumer surplus. So it may be that there are interventions which both raise consumer surplus and benefit the platform. Okay, so with that, let me stop and thank you for your attention.
Okay, thank you, Andrew. So Pan Hao is going to discuss the paper.
Okay, so let me share my screen. Is it working well?
Yeah, I can see it.
Okay, sure. Okay, hi everyone, Tat Hao here from the National University of Singapore. First, I would like to thank the organizer for inviting me to discuss this very promising paper by Andrew and his co-authors, Justin and Matthijs. I enjoy reading the paper and I have learned a lot from it. What I will do now is to first briefly summarize my understanding of the paper, and then I will give my comments. As mentioned by Andrew, the paper looks at the intersection of two important recent topics. First, we have the growing popularity of pricing algorithm in the online marketplaces and the potential anti-competitive role of such algorithms in the sense of these algorithms may facilitate collusion. Second, we have the ongoing policy discussion on the rule-setting roles or the platform design roles of these online platforms, in the sense that the platform can make design choices that influence the on-platform competition. in this context, given that collusion by pricing algorithm is a possibility, then the paper basically asks, can a platform design its recommendation system to mitigate this problem highlighted in the first point? The answer is yes. So the paper proposed two possible ways to look at it. First is the price directed prominence, PDP, and the second is dynamic price directed prominence, or dynamic PDP. The paper has a theory part and an experiment part. In the theoretical model, there are n firms engaging in the standard price competition with logic model. And then the firms have the game repeated infinitely many times. And then the paper basically compared three recommendation design. The first is the no design benchmark, where all n firms are shown to consumers. The second is the PDP, where, as Andrew mentioned, there are care firms with the lowest price are shown. In the case where the firms behave competitively, or in other words, there's no collusion, then the paper showed that introducing PDP compared to this no design benchmark result in lower price, which is good for consumer, but lower variety, which is bad for consumer. So depending on how these two things trade off, then the general effect to the consumer surplus is ambiguous. And then the paper looked at the case where collusion is possible, and they show that PDP basically makes collusion harder to sustain compared to the no design benchmark. However, the downside of PDP is that if firms are very patient, such that they collude with or without PDP, then the paper showed that the price decrease resulting from PDP is actually rather limited. And combined with the lower variety, the consumer surplus would decrease. So we see that whether PDP is good or not depends on whether the market is cartelized or not. So to address this problem, then the paper proposed this dynamic PDP. The way it works is basically the same as PDP. And the main difference is that the firm that sets the lower price in period T is being shown at period T, as well as getting an advantage that protects it from subsequent retaliation from rival in subsequent periods. So the main idea is to make it more tempting for firms to cheat in any possible collusive equilibria. So owing to this design, they show that dynamic PDP makes collusion unsustainable, even if firms are infinitely patient. And as a result of this, the dynamic PDP leads to significant decrease in price, some decrease in varieties, and the overall effect is an increase in the consumer surplus under some appropriate conditions. And then we have an experiment part of the paper where they do some reinforcement learning simulation focused on the case of duopoly. One thing to note here is that the setup of this experiment is slightly more generalized than the theoretical model in two ways. First, only a fraction gamma of consumer is affected by the recommendation. The remaining consumers see all firms as in the no design benchmark. And the second distinction is the recommendation is actually non-deterministic. Roughly speaking, it is that if the firms charge a lower price, then it will have a higher chance to be shown or selected for the advantage. In this experiment, then the author shows that the overall insights from these experiments are fairly consistent with the theoretical analysis, but at the same time, they also highlight some of the issues that specifically arise due to algorithm and learning. In general, my comment is that this is a very nice paper. It addresses some highly relevant issue while making some important contribution. There are three things I like about this paper. First is that there's this theme of, in platform design choices, there's a trade-off between price level and number of varieties. Such a trade-off has been looked at by several papers in the literature that look at recommendations or designs by the platform intermediaries. But as far as I know, none of them consider the possibility of cartelization. So a novel contribution here is the paper show how this fairly standard trade-off significantly changes once we take cartelization into account. The second thing I like is that there's this rather nice managerial implication whereby the platform recommendation design should take into account the possibility of cartelization. For example, the author proposed that the recommendation design should condition on the past pricing history rather than the current pricing. So in this sense, platform managers should think of designing rules that is robust to cartelization. And finally, what I like is the approach of theory plus simulation-based experiment. This is a very useful approach, I would say, to study how pricing algorithms respond to design choices by platform in general. And it could be applicable with or without cartelization. So I think this is a very promising approach for future study. Now let me get to some specific comments or questions. So in this figure one, Andrew have this figure showing that the proportion of consumers who are exposed to this PDP, how it changes the price. Then what I find is super intriguing is this early part, whereby relative to the known design benchmark or gamma equals to 0, a tiny amount of PDP actually increases the price. So this makes me wonder, is it because that this small gamma changes how the algorithms learn? Or is it because something that has to do with the theoretical foundation? Is it because small gamma somehow make it easier to sustain collusion? So one thing to note here is the theory model compares gamma 0 and gamma 1, whereas here you have something in between. So for me, I think it would be interesting to explore a little bit, like, what is there anything different in this in between? So such cases would probably be difficult to solve. So perhaps some sort of numerical simulation based on perfectly rational agents could be useful to understand like what's going on here. Okay, this relates to my second comments. So one of the main message from the experiment is that learning behaviors by the algorithms may lead to outcomes that contrast with the theoretical predictions. However, as I noted just now, there are some modeling features of the experiment setup that are slightly different from the theoretical model. So when I read the paper, that sometimes I was wondering to what extent the outcome difference are driven by the algorithms at learning rather than the difference in modeling feature. So I think this is something that could be useful to highlight. Next comment is this regarding dynamic PDP. So the theory predicts that dynamic PDP above cost pricing cannot be an equilibrium, at least under some conditions. So specifically, I refer to these two parts where this gamma is fairly close to 1, which is in line with the theoretical model. What we see from the AI pricing is that the observed price are substantially higher than the cost, the marginal costs. Even if the pricing algorithm is smarter. So a natural question here is, how are the algorithms actually sustaining this collusion or sustaining this above cost pricing? And it makes me wonder, is it actual collusion, or could it be some sort of a failure to optimize on the parts of the algorithms? So in order to shed light on what is happening here, like how do algorithms sustain this collusion, I think some form of anatomy of strategy, as in the Kawano paper, could help to shed light here, because I think it's important to distinguish between this failure to optimize or this collusion. Okay, it could be the case that the algorithms are just somehow playing suboptimally and they just coincidentally end up with a high price. Okay, and my last comment is regarding this platform profit. So you have this table showing various specifications and compare this critical growth elasticity for different recommendation system. The way I understand this table is the lower critical elasticity correspond to, it makes it easier to raise total revenue. What I'm interested in is the first comparison, which seems to suggest that dynamic PDP is more effective in raising total revenue. But for the subsequent comparison, I noticed that the PDP and the dynamic PDP, they are done with different parameters. So I think it could be useful to have a few more direct comparison between PDP and dynamic PDP to understand like which one is more profitable for the platform and something along those lines. And I think that's all from me. So thank you, Andrew.
Thank you, Tahao, for your discussion. Andrew, do you want to take a few minutes to reply?
Yeah, so thanks for the discussion. That was very, very helpful. Very, very good points. So maybe let me start with the differences in the, so you said that it's not clear whether perhaps it's the algorithms that are driving these differences or the setup. So it's true that the setup in the experiments is very slightly different from the theory model. Firstly, because we have this gamma. I guess there we can just think about gamma equals 0 and gamma equals 1. So that's a direct comparison with the theory model. But it's also true, as you said, this is something I skipped over in the presentation. So in the experiments, we also have a slight smoothing. Because in theory, we have continuous price space, whereas in the experiments, we have a discrete price space. So we were a little bit concerned that what would happen if two algorithms charge exactly the same price. Okay, so we wanted to have some randomness, which is parameterized again by a logit type model. And now we make that fairly sensitive to prices. So as soon as one firm jumps down by one increment, it's very, very likely to get demand, like in the theory model. So I sort of feel like that's probably not too important, but it's true that perhaps we should emphasize that a little bit more. So I'm sort of convinced that the differences are really driven by the algorithms rather than the setup, but we should emphasize that more in the paper. In terms of this non-monotonicity of the prices, the fact that price initially increases in gamma, that's something we've thought about, we've discussed a lot. We're still not entirely sure what is going on there. It could be, but this is just a conjecture, it could be, of course, that as you increase gamma, you're also changing what happens in a competitive market. So intuitively, we would think that you're probably going to reduce prices in the competitive market. And so if you think that these algorithms, it's not entirely clear how these algorithms, it's not entirely clear how they operate, right? But you might imagine that if we're reducing prices in a punishment stage, in a punishment game, then that might allow them to sustain higher prices in the collusive subgame. And so that might explain why, at least initially, prices increase. And then, as we've said, when gamma is sufficiently high, we know from the theory model that prices should tend to be lower. And that seems to be what is happening. So that would be my take on it, but we're not entirely sure what is going on. We're not entirely sure how we would get at that, but I agree it's very interesting, and it's a robust pattern. It happens in a lot of these graphs, actually, in the paper. In terms of, so you said that dynamic PDP theory, simple theory would predict that price should go down to marginal cost. And of course, that's not true. That's something I didn't highlight in the talk, but this is, of course, another interesting difference between what simple theory predicts and what the algorithms actually do. At the same time, I guess I would point out that I agree that, of course, theory would predict prices should be lower. At the same time, because we have this discrete price grid, remember that if we did the theory with a discrete price grid, we wouldn't actually get price equal to marginal cost. We would actually get price equal to one increment, which would be about 1.08. So if you look at it, it's true that prices are not going down to what theory would predict, but I think they're not that far off. But there is a small margin, I agree, a couple of price increments. And I agree that may be because they're failing in that case to compete. So there may be some noise where they're, as you said, they're not optimizing, they're not learning to compete. So there's this question of whether they learn to collude or whether they learn to compete. And there, I think it's reasonable to think that they were colluding. The intervention has now pushed prices down, but then there's a failure to compete at the margin, which means they don't go all the way down to what theory would predict, which would be one increment. I don't know if that makes sense.
I see. But in any case, I think some sort of description, like what are the strategies actually played by the AI would be super interesting there. Yeah,
I agree. That's something we should think about. And then I also agree for your point about platform profits. That's something we should do. We should look at more. We have a lot of results, so we just put some in the paper, but I agree we should probably do that more systematically. It would be interesting to see which of these two interventions is better in practice for the platform. Yeah, but thanks for the comments. They're very, very good comments. Thanks.
Thank you.
All right, thank you to you both. So we still have around 10 minutes, so I will open the floor for Q&A sessions. So if you have questions, can you just unmute yourself and ask directly to Andrew?
Hi, Andrew.
Oh, Gao Ming, you go first.
Oh, okay. Thank you, Kim Zhao. Hi, Andrew. I was wondering, do you know if do you know how platforms might implement dynamic PDP? I mean, the type you proposed in the theory part, do they actually use it, or do they use like a variant of it, or do you know? Have some sense?
So if I think about Amazon, it's very hard to know exactly how Amazon decides which sellers are made prominent or not. There's a lot of debate about this. One thing that we did find, which we think is nice, is that there's someone at the European Commission called Nestor Dutch Brown, who has some data from the Amazon buy box. So on Amazon, if I search for a product, there's some algorithm which decides on the ranking, but then even conditional on a product, there's another algorithm which decides which seller should be made prominent. So they scrape some data for this buy box, and they try to work out how that buy box is allocated. And so what they find is that having a low price is, of course, more likely to get you the buy box, but they also showed that past performance matters. So even if I don't have the lowest price today, if I had a good recent past performance, in their case, it was to do, I think it was with sales, but of course, sales would be a proxy for, high sales would be a proxy for a low price. So of course, we don't exactly know how these algorithms work, but there does seem to be some evidence that they are backward looking. Of course, not exactly what we have here, but kind of in the same spirit.
I see. And it's just to follow up on that. In the theory, you only looked at the case when the PDP shows just one seller, right? If I understood it correctly. Yes. Okay. Then is it? I guess Kim Zhao asked this related question about the number shown earlier, but is it is it not tractable to look at like other cases, like a general number of sellers being shown? Or I mean, I just want to understand why you focus on this one seller case, because it's, to me, across different let's say screens, like let's say on a mobile phone or on a computer screen, you probably have a different constraint on the number of sellers that could be easily shown, which potentially could affect both, I mean, theoretically, and also probably for AI learning. So I just was wondering.
No, I think this is a very valid concern. I guess, so there are two reasons why we did that. So first of all, it turns out if you look at the paper, the proof, even for showing one firm, is actually quite complicated, and it took us quite a lot. I mean, we sort of had the intuition that this would work with one firm, and we also have the intuition that it's going to work with multiple firms, but actually proving that formally was a little bit harder than we expected. So we sort of think we could do it, but we haven't got around to doing it yet. So that's kind of one reason. Another reason, though, is that in the experiments, because it's quite hard when you have a large state space to run these experiments, we looked at simple cases with just 2 and 3 firms. And so clearly, if we only have 2 firms, then it only makes sense if you're only showing one firm anyway. So that was another reason why we didn't feel it was necessary to try and prove that result for more firms. But if several people think we should do that, then that's of course something that we should probably think about. And probably with enough work, I think we can do it. And as I said,
I'm not suggesting that you do it. Yeah, it's just something I was thinking about, the different screen sizes. But yeah, thanks for.
I mean, my intuition would be that the same result will go through, and then of course the consumer surplus effect will be even stronger. It's already very strong. I didn't put formal details on the slides, but it's already very strong. I would expect it would be it would therefore be much, much stronger, even for very, very large number of firms. Just showing a couple would lead to large consumer gains.
I see. Thank you.
Andrew, I guess I'm following up on our echoing Tech House comment. I'm wondering, because when you're calculating the theoretical outcome under collusion, I imagine that, for example, the collusion, when you deviate, we punish you by reverting to Nash. That I'm not sure. I'm just being slow. I'm not challenging, but I'm just not sure that that particular strategy can be implemented by an algorithm using Q-learning, in particular when the states are being defined as the last period price. So, for example, I'm just a little bit slow to see that that particular way to define the state space can code whether we are in a punishment phase or not. So in case we cannot code that, today we are in a punishment phase, then we may not be able to implement the theoretical punishment, and hence we cannot sustain the theoretical collusive level. So maybe there's nothing to do with learning or what's the term you use, a learning challenge or something like that. Maybe it is just a theoretical limit. The limit is given by the fact that the state space cannot code certain things.
Okay, so that's a very, very good question. So I guess I have several answers. So you're correct. So there is a paper, I forget all of the co-authors. There is a paper in Econometrica by Hamid Saburian in Cambridge and some co-authors, where they show that if you have a sufficiently, so basically if you have a continuous price space, then one could code in that information. Now, of course, as you point out, we don't have a continuous price space. We have to discretize the price space. And so it's true that they cannot perfectly tell that. And I think that's another reason why we get differences between what the simple theory would predict and also what the algorithms do. So I completely agree. Now, the reason why, of course, we can't have a very rich state space is just because it would, the problem would not converge. Right? Already, it takes a long time sometimes for it to converge, even with the simple state space.
Thank you.
But that's a very good comment. Yeah.
We still have time for one more question. So is there any other questions? Okay. So if there's no more question, I'm going to call off today. And so let's thank again Andrew and Tahoe for the presentation and discussion. And thank you very much for giving the presentation and discussion, especially Andrew. Now at 7:30 in the morning. Thank you. Let's applaud.
Thanks.
Thanks.
Thank you, Andrew.
Thank you, Andrew.
So we welcome you to come back in a week. So Tahoe is actually we're presenting in our next seminar on platform governance, and we will hope you can join us in a week. So see you.
Thank you. See you.
Thanks.
Thanks.
Thank you.
Bye-bye. Have a nice day, Andrew.
Thanks.